Okay, so in this unit, we're going to talk about linear approximation and differentials. So go ahead and write that at the top of your page. Remember, I do check your notes, so make sure you have everything I wrote down needs to be down in your notes as well. So, and differentials. Differentials. There should be an S at the end. Sorry, I can't squeeze it on. So a linear approximation allows us to look at any curve that we have. So for example, the curve can look like that. And we can pick any point on our curve, say right there. And then we can approximate like around our curve, the shape of, around our point, we can approximate the shape of our curve with a line. Okay, so you can think of it very similarly to a tangent line. The difference is that a linear approximation can intersect your curve more than one time, whereas a tangent line couldn't. Okay, so in this class, they're almost always, every linear approximation you do will almost always be a tangent line as well. But no, when you get to multivariable calculus and those higher levels of calc, that's not always the case. Okay, so that's a linear approximation where you're approximating the shape of the curve with a linear function. Okay, so remember, we always write like our linear functions in this class in point slope form. Okay, same thing. So then your differentials are important because they allow you to calculate how much error is in your linear approximation. So let me just zoom in on this picture so we can get a really clear idea of what's happening here. So the blue line right here represents the point I wanted that my linear approximation to go through. Now I can pick any other line on any other point on my line, so I'm just going to pick some random point up here. Okay, it doesn't matter. There's always going to be some error. So for example, just on my curve, I have this point and then this point, which my purple line is close to. Okay, those are pretty close together, but the black one's on the curve I want, and the purple one's the approximation. So if I think about this in terms of slope or derivatives, okay, I know that my x distance, I know that my x distance here is my change in x, which in this case, and which always will be true, is the differential of x, okay? Differential just means change in. It's a pretty fancy word. Now, we're gonna if we go up vertically from here, our change in our line is dy, okay? Which is this whole thing. But if we just look at the change of our function, so this change, we would have our delta y, okay? Because that would just represent the change in our black curve. So we our linear approximation has this error right here. Let me get a different color. Right here. So this portion is the extra, so that's what we would call the error. Okay? And your error in this case is always going to be your differential of y minus the change in y. So again, the differential represents the change in your line. The delta y represents the change in your curve. Okay? Again, differential y, so dy is the change of height in our line. Delta y is the change of height in our curve. Okay? Because our x value was the same, right? Or in this case, our delta x represented our differential of x. And if you recall, the slope of your tangent line is always your derivative, right? And we know that your derivative, so like y prime, for example, is the same thing as writing dy over dx, which if you look at in your picture, dy is your change in x, dx is your change in x, and dy is your change in y, okay, which is how you get the slope of your tangent line, or this other form for your derivative notation. Okay, so let's just hop on in and do an example so you can kind of get a feel for what's going on. So let me just move the page down. So here we are. So for our example, I want you're given, let's not use blue because that's going to be a bad color for you guys to read. Hang on. Okay. Example 1. Given f of x equals, how come I don't have an equal sign? There we go. Equals 15 minus x cubed find the linear approximation at 2 comma at the point 27, sorry. Okay. So that's what we're going to do right now. So first of all, I don't know what 15 minus x cubed is. I don't know what this function looks like, but it doesn't matter. If you want to go ahead and graph it to give you kind of a visual of what's happening, totally feel free to do so. I'm not going to do so, but you're welcome to graph that in your calculator and kind of see what it looks like at the point 2 comma 7. So we're already given a point, and we know that for our linear approximation needs to be a line. So pretty quickly you should realize that, okay, well, 2 is going to be x1, 7 is going to be y1, so now we're left to find our derivative, or our slope, which you should remember is the derivative of this function. So I'm going to start off by finding y prime, or f prime of x in this case. So f prime of x would just equal negative 3x squared, right, if I differentiate my function. Now, I don't need f prime of x at every point. I just need it at my x value that I'm given. In this case, it's 2. So f prime of 2 would equal negative 3 times 2 squared, which is going to equal negative 12. So that would mean my slope is negative 12. So when I plug my slope and my point into point slope form, that would end up with y minus 7 equals negative 12 times x minus 2, okay? Now, linear approximations, we always solve for y. It's really important that y is isolated here. So we don't need to distribute 12 like you probably want to do because you see parentheses and your Algebra 1's teachers trained you well. We just need to bring 7 to the other side. So when I do that, I'd end up with y equals 7 minus 12 times x minus 2. And that is your final answer. What's important to notice about this answer is this form that our answer is in actually gives us some very valuable pieces of information. So for example, the 7 that I have right here is f of 2, right? When I plug in 2, I'd end up with 7. If I plugged in 15 minus 8, I'm at 7 to my original function. So I can rewrite 7 as f of 2, okay? 12 is my slope, which I got from my derivative. So I can just write that then as minus f prime of 2, and then x minus 2. Now this is helpful because it allows us to think about our linear approximation just in terms of what we're given in our original function. So if we were to write this out more broadly, we would say, let me get a different color here. Like the linear approximation at a point x equals c, sorry, where's my eraser? At a point x equals c on the function f of x is y equals f of c plus f prime of c times x minus c. Okay, so this is actually the form of a linear approximation you always want to use. In fact, you can go ahead and even write that as like your definition or your property of a linear approximation. Okay, so that's it for these notes. Go ahead, write down any questions you have, and we will discuss them and do some more examples next time I see you guys in class. Also, you have a very short video just on notation of an integral on section 5-4 that I also need you to watch now.